Hello, everybody. Welcome to the Deep Learning Models in Production ML Engineering Perspective presentation. So a few words about myself. I'm Julia. I work as a machine learning engineer at Fandom. At my previous job, I was a data scientist in cybersecurity company. What I like in my job is making AI solutions work, bringing models to life, and being part of the amazing team as well. In my free time, I'm a singer, songwriter, and a dog mom. Before we start, I would like to share a few words about what data science and machine learning is here at Fandom. So, as many of you might know, Fandom is a massive collection of articles written by fans about their fandoms. If you don't know still what Fandom is, I bet you've been on this website at least once. For example, if you Google your favorite character, like Geralt of Rivia, in Google search, you will most probably end up on our website. So our main and most major project that involves machine learning is content classification. So we are categorizing every article that we have, and we have 40 million of articles in total, into meaningful categories. So for example, for this article about Geralt of Rivia, we would assign such labels like vertical type of books, video games, and movies, a page type of a character, or a video game genre RPG, which has a number of meaningful business applications, from ad targeting to enriched analytics to content recommendation. We're also doing more fun things, from recommendations through various experiments involving GenAI recently, but this is outside of the scope of today's presentation. I also would like to make sure we all understand what we mean by data science and ML engineering here at Fandom. So we have two teams that all together form up the full ML model life cycle. And we have this theoretical diagram that's states that the ML model starts from a business need. It goes through knowledge, insights, prototyping, optimization, up until availability on production. And what data scientist does is to focus mostly on the left-hand side, and the engagement slowly fades out as we reach availability and maintenance. And for ML engineer is the contrary. So we're focusing on the right-hand side. Or we can also make it a bit simpler for now and just assume that data scientist is responsible for training the model by using tools such as Jupyter Notebook or PySpark. And then the model is handed over to the ML engineering team that will deploy the model to production using the infrastructure that we're also maintaining. Great, so I hope this makes things clearer. So now what is the story for today? We have a new task to deploy 6 new content classification models that have shown significant improvements of key metrics. So these new models are different to the previous ones. So namely, they run on GPU. Each of them is half of a gigabyte large, and they take more time to compute as well. So more specifically, they are deep learning models that consist of BERT embeddings layers followed by a classification layer. As you already know, there are 40 million of articles to be classified, which is quite a massive amount of data. When we use the basic escalator models, and if we only had one machine, it would take 5 days of processing. And at the same time, we don't have time and resources and don't want to invest in building our own ML platform. That would be an end-to-end solution. And we need a scalable and reusable solution for now for some rapid prototype deployment. So the plan is we will use a managed solution for now, one of the functionalities of AWS SageMaker. We will avoid time-consuming infrastructure setup by using so. and we will deploy the models quickly. So now, what the ML engineer plan to do in this case? We will follow the same steps as usual. So first we will fetch the model from the MLflow platform. Then we need to prepare the environment to operate the model in production. And then we will run batch transform with SageMaker, which is the managed solution that we decided to start with. Okay, sounds like a plan. So let's go. First thing that we need to do is fetching the model from MLflow platform. So if you don't know the tool, I highly recommend you to check it out. It's an open source solution for keeping track of experiments and managing the models registry as well. So we ML engineers are mostly using the models registry part. So when a data scientist logs the model to the MLflow via MLflow client, it automatically creates files that are important for us, such as requirements.txt, which describe the environment in which the model was trained. So at this first step, we already encountered a first hiccup because now the models are 2,000 times larger than before. And by before, I mean small sklearn models, which turns out to be pretty network traffic heavy. So eventually we had to adjust the client server configuration of the MLflow web application to be able to proceed here. All right, so now we can proceed to preparing the environment. And by environment here, I mean the Python code that will define how to run the inference with this model, supplemented by the Docker container that needs to be very specifically adjusted for the model in terms of CUDA driver, PyTorch version of Python, a couple of different libraries as well, and config files. So we have seen it to be very sensitive to versions change up to the point that it will prevent you from even loading the model onto a GPU. Also, the Docker containers themselves have grown in size, so they are now 5 times larger, up to 7 gigabytes of size, which is again much harder to upload and download. And even in terms of storage, this is simply much more. All of this combined with the fact that you probably don't have a GPU processing unit on your computer makes local development pretty cumbersome. So at the moment, we're really leaning towards moving even the local development to the cloud. But all right, we also tackled the second step. It took us a little bit more time than we planned. So now we can proceed to the third step that is about running the SageMaker batch transform. So we already know that we have 40 million of articles, but what is the actual input that we want to process? So we group the articles into files of 2 megabytes each, roughly. Every file contains multiple rows. Each row represents a single article, and these files are plain CSVs without the compression. So what exactly we would like to do with all these files? We simply want to apply the model on every file, and we don't want to wait many days for the results. We really would like the results to arrive in a couple of hours. So how can we approach this? If you have a compute cluster that consists of a number of instances that will just do the job independently, we will be good to go. But in this kind of a setup, you probably would like to ensure that every instance will be equally loaded with work, so you don't have an instance that is waiting and wasting your money as well. So it'd be nice to have a mechanism that will simply handle all of this for you, which is what SageMaker batch transform can do, provided that you create a special SageMaker model for inference object that will contain everything that we prepared so far, which is the Python inference script, the Docker container, and the model itself. So interestingly, you don't have to put the model inside the container by yourself. This is another thing you don't have to worry about, and SageMaker will just do the magic. Yeah, so another comment on the SageMaker magic, because by using batch transform here, we really skipped a number of layers that we would have to care about if we were creating the infrastructure from the bottom. So the entire compute cluster setup needs its configuration. We would need an orchestrator for this system, a processing jobs queue, load balancing, and even managing the actual machines, making sure they're created, recreated, and destroyed after we're done. Not to mention all the AWS permissions that would also have to get together very well. So that's why I call it the magic service. You don't even have to know that these problems exist. It also scales up and down arbitrarily. You just change one number and you have more instances to process, and you speed everything up this way. So how does it play with these 6 models that we have? It turns out it works pretty well. This is a code snippet of how you can use the batch transform, provided you have this SageMaker model object. We just have to go through all 6 models that we have, and it's really a great fit for the rapid deployments that we need at the moment. SageMaker functions also have some flaws, but as I said already, we're in the situation that we're really aiming for this kind of a solution. So cool. And so far, so good. We ran the batch transform and it worked. So we're really happy about this. But yeah, now it's time to compare to any other efforts we did previously with older models. So we checked out this batch transform that we newly ran. And it turned out that we now pay 10 times more compared to batch transform over all the articles as well, but with some small sklearn model, for example, some random forest classifier. So why did we increase the cost? So first of all, the price per hour for AWS instances with GPU is higher, and also the compute time took longer than before. So that's not bad because we tagged the articles, but it's also not so good if you want to continue using this in production, right? So this is where ML engineer is super excited to come into action and simply optimize what we just did. So now the plan is we will check out the matrix of the instances that have been working on this processing. We'll optimize the code, test this code on some representative sample of the entire article's corpus, and we will repeat it if we still have some ideas to speed things up. So first thing that we need to do, we prepare this representative sample that is only 2.3 gigabytes large. And we take the inference code as it is, and we just run batch transform on a single instance. So this way, it took 3 hours and 12 minutes, and we assume this is the benchmark for now. So what you see here, this graph has been auto-generated by SageMaker batch transform, which is another pretty cool feature of this service. And it lets you view really quickly some critical performance metrics of the instances that have been doing the job for you. So what we're paying the most is GPU utilization, and you can check out the GPU utilization in percent over time during the time range in which this batch transform was being executed. So ideally, we would like to use the GPU at 100% as much as possible, because that's why this is what we're paying like 8 times more for example, when you look at this prices per hour. But what do we see here? It's definitely far from perfect. And if you look at these like red lines, for example, we have a number of GPU downtimes that really suggest that there is a field of improvement here. But also you should notice that the CPU utilization is actually 100% all of the time. That makes us think that maybe GPU is much faster than CPU, which is doing some work. And that GPU might be actually waiting for CPU to finish some data preprocessing. So let's have a closer look about what's going on underneath. We're thinking about this critical point as the GPU unit with the model loaded. But what the model here is expecting is an input encoded into tensors of numbers, while our input is some plain text, content of the articles. And this is the CPU's responsibility to prepare the data so that it turns into numbers. So CPU has to do the tokenization job followed by the encoding job. And what's even more, it has to formulate a batch in order to use the GPU efficiently. So more specifically, what is the batch? This is a very simplified example of what a batch is, which is a sample, which is a set of samples, each of which needs to have the same length. So in this case, a batch is some sort of a rectangle, which in real life has more dimensions than 2. And you should really use batching when you're using the GPU, because this is what they are designed for. GPUs are best at matrices multiplications that make them a perfect fit for graphics and neural networks. So the worst thing that you would do here is to input the article 1 by 1. So this is a must, especially that, notice we're not working with an endpoint here. We have all the data already available. So the idea is simple, and it's a first step that you would usually take. We'll just use multi-threading because we have seen it's a lot of work for CPU to prepare the batch, but maybe if we use all cores of the CPU, we'll increase the chance that GPU won't have to wait, because we will have 4 workers preparing another batch. So GPU will have something to choose from all the time. If you're working with PyTorch and want to enable that, it's very simple. If you use PyTorch data loader and use the dedicated parameter for that. Cool, so we make a second run after we add the multi-thread data loader, and we have decreased the time from 3 hours and 12 minutes to 2 hours and 11 minutes, which is not bad. It's definitely promising. But if you look at the graph, it's not what we really wanted to see, and GPU is still waiting for some reason. So we probably can dig deeper in order to improve what we really would like to see, the GPU utilization to be more constantly at the level of 100%. So another thing you can do is better understand the data that you are working with. So if you think about this tokenizer that is working on a CPU, it has a number of steps, first of which is splitting the text into words or tokens, but I'm simplifying it into words for this presentation. And then it only takes 512 first words, because this is the requirement of the batch to have every sample have the same length. So that then we will just propagate it through the network. However, some of the articles on Fandom, including Geralt of Rivia, are much longer than 512 words. For example, this article is around 15,000 of words long, so it's definitely a long read, which means if the tokenizer is not very smart, it first applies the tokenization logic over the entire article, and then it only takes first 512 words. So we did a lot of work on CPU, and then we just throw the remaining words away. Because of that, the idea is we'll just truncate the input text beforehand without having the tokenizer to do all the analysis over the entire text. So sounds like a good idea. So let's see how it worked. And it turned out that we have improved the GPU utilization graph pretty visibly. And also the time now has decreased to 1 hour and 31 minutes. So this is even better than before. We're already halfway down in the execution time. But the ML engineer doesn't stop. So what if we apply similar logic, but we will think about the GPU right now? Maybe there's something more in the data that we should be aware of. So it turns out that some articles are way shorter than 512 words that we assumed at the beginning. And if you browse the Witcher wiki, you can find an example, for example, an article that is titled Pigeon, and it only says that you can find pigeons in the Witcher 3 Wild Hunt game somewhere in the city of Novigrad. And this is the end of this article. So we are still tagging it. And what happens if the article is so short? The tokenizer needs to make the article meet the requirement of the batch size to be of this 512 words long. So if it's not long enough, it has to pad it with a special token. So in this example of a very small batch with a short length of like 12 elements, suppose we have both short and long examples in this batch. And in order to have this form of a rectangle here, we need to fill all the empty gaps with the pad special token that basically doesn't tell anything more for the BERT transformer that we are using. But what if the batch was half of size and we only happen to have these first short articles in the batch? Basically, if you start from the middle of this batch, we are not providing any more information to the neural network, but we'll still be performing some computations related to these unnecessary words because we included them in the sequence. So with these two samples, we could actually just keep the length of the batch up to the longest sample that we have. So I was a bit skeptical about this one, but we planned that we will group short articles together and reduce the batch size. And this way we want to maximize the chance that we will really shorten the batches. And we want to pad only to the longest sample in the batch, so changing the padding strategy. So will it work, or is it too complicated? So it turns out that we saved another 30 minutes with this improvement. So we saved another 30 minutes and we finally went from 3 hours, 12 minutes to 1 hour and 2 minutes. So just wrapping this up, we started from 3 hours and 12. Then we added parallel data preprocessing on a CPU and we were 1 hour down. Then we added this input text truncation before tokenizing. And then we proceeded to the smart batching, followed by reduction of the batch size. And now we're at the level of 1 hour and 2 minutes. So we reduced the compute time 3 times on this representative sample, which also means reduce the costs 3 times. And the model quality didn't even change. So notice that we didn't apply any more sophisticated solutions for speeding out the model for inference, such as quantization, that actually changes the behavior of the model. We only did some smart tricks here. So hooray, that's a success. This is something that we're really proud of because to me, this reduction is pretty massive. So wrapping this up, we talked about what ML engineering does in practice in Fandom, and what is special about deploying deep learning models and how are they different to smaller ones. And we also talked about what you can do to reduce the costs of using GPU for batch processing. So this is all I prepared for today. Big kudos to everyone involved in this project. Here's the entire ML engineering team that consists of 3 amazing people, Jacek, me, and Wojtek. Thank you very much.